Welcome to this session on Mathematics, Chapter 2 on Polynomials for Class 10, Grade 10. We are covering relationship between zeros and the coefficients of a polynomial. In this session, we shall be talking about the relationship between zeros and the coefficients of a polynomial of type linear, type quadratic, cubic, quartic, and also we shall give the formulae of relationship between zeros and coefficient for a polynomial of general form of degree n. Let's start with the linear polynomials, and we know that linear polynomials will have at the most one zero, and let's represent that zero by letter alpha. Also, the linear form of the polynomial is ax plus b, which once solved will give us the value of the zero of the polynomial, that is alpha, as equal to minus b by a. Now this equation is our relationship between the zeros of the polynomial and its coefficients. Let's now talk about the quadratic polynomials. We know that a quadratic polynomial will have at the most two zeros, and let's represent those two zeros by the letters alpha and beta. If alpha and beta are the zeros of the polynomial, then x minus alpha and x minus beta will be the factors of the given polynomial. Therefore, we shall be able to write the polynomial ax squared plus bx plus c equal to k times x minus alpha times x minus beta. Here you notice that x minus alpha is a factor of the polynomial, x minus beta is a factor of the polynomial, and k is a constant term. And of course, a is not equal to 0, because if it were to be 0, then the polynomial will no longer be a quadratic polynomial. Once we simplify the right hand side, we get ax squared plus bx plus c is equal to k times x squared minus k alpha plus beta x plus k alpha beta. Now let's compare different terms in this equation, or the coefficients of x squared, coefficient of x, and the constant term on both sides of this equation. Once we compare the coefficient of let's say we compare the coefficient of x squared, we notice that the coefficient of x squared on the right hand side is k, and on the left hand side it is a. Therefore, we get the equality a is equal to k, and let's call this as our statement number 1. Now let's compare the coefficient of x on both the sides. The coefficient of x on the right hand side is minus k times alpha plus beta, and on the left hand side this coefficient of x is b. So if we compare these two coefficients, we get alpha plus beta is equal to minus b by k, that is equal to alpha plus beta is equal to minus b by a. And of course, we are using here the fact that a is equal to k, which we deducted or deduced from the statement number 1. Similarly, if we compare the constant term on both the sides, we get k alpha beta is equal to c, that is c is equal to k times alpha beta, and this gives us alpha beta is equal to c divided by a. So now if we summarize our understanding, or what we have deduced so far, we can say that alpha plus beta is equal to minus b by a, which is equal to minus coefficient of x divided by coefficient of x square, and the product of the zeros, that is alpha times beta, is equal to c by a, which is equal to constant term divided by the coefficient of x square. And let's take an example of the quadratic polynomial. Let it be 2x squared minus 4x plus 1. In this case, a is equal to 2, b is equal to minus 4, c is equal to 1. Therefore, our sum alpha plus beta, sum of zeros, will be minus b by a, which will be equal to minus of minus 4 divided by 2, which is equal to 2. Similarly, the products of the zeros, alpha times beta, will be c by a, and in our case c is equal to 1 and a is equal to 2. So c by a, that is product of the zeros, will be 1 by 2, which will be equal to half. Now let's take to the next level, and let's talk about the relationship between zeros and the coefficients of the cubic polynomials. We know that a cubic polynomial will have at the most 3 zeros, and let us show them by 3 letters, alpha, beta, and gamma. And if alpha, beta, and gamma are the zeros of the polynomial, then x minus alpha, x minus beta, and x minus gamma will be the factors of the given polynomial. Therefore, we shall be able to write the given polynomial ax cubed plus bx squared plus cx plus d as equal to k times x minus alpha, x minus beta, x minus gamma, where you can notice that x minus gamma is a factor, x minus beta is a factor, x minus alpha is a factor, and k is a constant term. So we will simplify the right hand side, and we get to write this right hand side as kx cube minus k times alpha plus beta plus gamma x square plus k times alpha beta plus alpha gamma plus beta gamma times x minus k alpha beta gamma. So now if we were to compare both the sides of this equation, we can compare the coefficients of x cube, x square, x and the constant term, or we can compare different, or we can say that we are comparing different terms on both the sides. We notice that on comparison of coefficients of x cube, we get a is equal to k, and let's call this as our statement number 1. Similarly, if we were to compare the coefficients of x square on both the sides, we notice that on the right hand side the coefficient of x square is minus k times alpha plus beta plus gamma, and on the left hand side the coefficient of x square is b. So if we put them both equal to each other, we get alpha plus beta plus gamma is equal to minus b by a. Similarly, comparing the coefficients of x, we get alpha beta plus beta gamma plus alpha gamma is equal to c by a. And if we compare the constant term, we get alpha beta gamma is equal to minus d by a. And of course, in this comparison, we are using the term or the statement number 1, which is a is equal to k. So if we summarize our relationships between zeros and the coefficients of a cubic polynomial, we say that sum of zeros S1 is alpha plus beta plus gamma is equal to minus b by a. Second sum of zeros S2 is equal to alpha beta plus beta gamma plus alpha gamma is equal to c by a. And finally we have alpha times beta times gamma is equal to minus d by a. And let's see an example, which is x cube minus 6x squared plus 11x plus 6. And this is of the form ax cube plus bx squared plus cx plus d. Here a is equal to 1, c is equal to 11, b is equal to minus 6, and d is equal to 6, which gives us the first sum of zeros as s1 is equal to alpha plus beta plus gamma is equal to minus b by a, which is equal to minus 6 divided by 1, but this has to be taken as a minus, so we get it as 6. Similarly, second sum of zeros will be s2, which will be equal to alpha beta plus beta gamma plus alpha gamma, which will be equal to c by a, and in our case it will be equal to 11 by 1, that is 11. Similarly, product of zeros alpha beta gamma will be minus d by a, which is equal to minus of 6 divided by 1 in our case, and hence it gives us minus 6. Let's now move on to quartic polynomials. These are the polynomials which have degree 4, and they are sometimes called as biquadratic polynomials. Their general form is ax4 plus bx cube plus cx square plus dx plus e, where a is not equal to 0. And now let's represent their 4 zeros as alpha, beta, gamma and delta. Their first sum of the zeros, that is S1, will be equal to alpha plus beta plus gamma plus delta, will be equal to minus b by a, that is minus of the coefficient of x cube divided by the coefficient of x raised to power 4. Similarly, the second sum of the zeros will be S2 will be equal to alpha beta plus beta gamma plus gamma delta plus alpha gamma plus alpha delta plus beta delta. This will be equal to c by a. The third sum of the zeros, S3, will be equal to alpha beta gamma delta, alpha beta delta, beta gamma delta, and this sum will be equal to minus d by a. And the fourth sum of the zeros will be S4 will be equal to alpha beta gamma delta, and this will be equal to e divided by a. Let's now move on to general form of polynomials. We know that the general form of polynomials is represented as a0 x raised to power n plus a1 x raised to power n minus 1 plus a2 x raised to power n minus 2 and so on up to an multiplied by x raised to power 0. In this form, an is not equal to 0 and n is a non-negative integer. We also know that a polynomial of degree n will have at the most n zeros. So let's represent those n zeros by letters alpha 1, alpha 2, alpha 3, alpha 4 and up to alpha n. Also, if alpha 1, alpha 2 and up to alpha n are the zeros of the polynomial, then x minus alpha 1, x minus alpha 2, x minus alpha 3 and so on up to x minus alpha n will be the factors of the given polynomial. Therefore, we can write the given polynomial to be equal to the multiplication of these factors and this whole multiplied by a constant term a0. So we have now an equation, that is the given polynomial is equal to the multiplication of its factors. So we can say that the given equation is a0 times x raised to power n plus a1 multiplied by x raised to power n minus 1 plus a2 multiplied by x raised to power n minus 2 and so on is equal to the a0 times x minus alpha 1 times x minus alpha 2 times x minus alpha 3 and so on up to x minus alpha n. So this is our equation where we have different coefficients of different powers of x. So now let's start comparing the coefficients of different powers of x and let's see what do we get. Let's now start comparing the coefficients of different powers of x on two sides of the equation 1. Let our first coefficient for comparison be the coefficient of x raised to power n minus 1. This will give us the first sum S1, which is alpha 1 plus alpha 2 plus alpha 3 and so on up to alpha n. And in simple form, it is written as sigma alpha I. And this sum will be equal to minus a1 divided by a0, which is equal to minus coefficient of x raised to power n minus 1 divided by the coefficient of x raised to power n. Next, let's compare the coefficients of x raised to power n minus 2 on both sides of the equation 1, and this will give us the second sum S2, which is equal to alpha 1 times alpha 2 plus alpha 1 times alpha 3 plus alpha 1 times alpha 4 and so on. And in simple form, it is written as sigma I not equal to j alpha I alpha j, and this sum will be equal to minus 1 square times a2 whole divided by a0. Next, let's compare the coefficients of x raised to power n minus 3 on both sides of the equation 1, and this will give us the third sum S3, which is alpha 1 alpha 2 alpha 3 plus alpha 2 alpha 3 alpha 4 plus alpha 3 alpha 4 alpha 5 and so on. And the simple form of this sum is sigma I not equal to j not equal to k alpha I alpha j alpha k, and this sum will be equal to minus 1 raised to power 3 a3 divided by a0. And similarly, we can find fourth sum, fifth sum and so on. But what will be the general nth sum here? Let's see, or let's find that out by comparing the coefficients of x raised to power n on both sides of the equation 1. The nth sum Sn will be equal to alpha 1 alpha 2 alpha 3 and multiplied up to alpha n, and this sum will be equal to minus 1 raised to power n an divided by a0, which is equal to minus 1 raised to power n times the constant term divided by the coefficient of x raised to power n.